So guys, welcome back. Today we continue with split algorithms, and we will talk about augmented Lagrangians and ADMM, matrix splitting, and other algorithms. So if you remember last time, we ended with the augmented Lagrangian, and we said that one of the drawbacks is the fact that when you add this penalty with the row term, the L row, the Lagrangian L row, becomes not separable, even if f of x is separable. So we would need more steps to keep the advantage of separability. So in fact, all what we've seen till now is just kind of preliminary to what will be seen now, which is the most important thing in this section, which is the ADMM. Okay? So the idea of the ADMM is that we have to define an algorithm that stands that uses the idea of splitting, okay, of separability. So in fact, ADMM stands for alternating direction method of multipliers. The original f of x, in fact, with the ADMM is broken into two parts. You may possibly want to call them f1 and f2. Okay, so you see from the beginning, we are splitting or separating the function in two parts. Okay, in fact, it's not exactly separability as we've seen a couple of slides ago. So to avoid using subscripts and getting confused, let us call them f and g. Okay, so f is for f1 and g is for f2. So two functions, f1 and f2. And we'll do also the same for x. So even though we'll put the condition that x is equal to z, in fact, we will give to g, the function g, we'll give it the new variable z. Okay? It's just a kind of mirror variable. Okay, just to notice the fact that we're working with different names. Okay, so we'll add the constraint that x equals to z. In fact, this allows us to keep a separable problem and compute, and compute xk plus 1 and zk plus 1 separately on parallel computers. So you see how parallel computation is quite important in these cases. Okay, the same steps still lead to maximization, and the penalty constant row becomes, in fact, an appropriate step size s. Okay? So in fact, the new constraint that you will add, which writes as x equals z, joins the original ax equals b conditions in a total p linear constraints ax plus bz equals c. Okay, so this condition ax equals b is transformed to ax plus bz equals c. Okay, so this is these are the main ideas of the ADMM method. Okay, preliminary. So just to summarize, we're splitting the function f of x in two, and even using a different name for x when it goes to g. So we'll be, in fact, trying to do what? To work on f of x plus gu z. So now we are maximizing what? F of x plus u z with an augmented Lagrangian for safer convergence. We said in the definition of augmented Lagrangian last time that we add this term we see here, okay, for safer convergence. In fact, to avoid having large errors, to get faster, close to the solution we are targeting. Okay? So you see, this is in fact like minimizing the distance, the square of the distance. So basically, you're avoiding, in fact, large errors. So let's read this Lagrangian. So L row now writes as f of x plus gz plus what? Plus the yt's, so the multipliers multiplied by ax plus b minus c. So usually this is the Lagrangian from the beginning. Now the only difference is that we added the row here multiplied by the norm of aux plus b minus c squared. Okay? And the key advantage, in fact, of the ADMM is that x and z are updated sequentially and jointly. Okay? So the two functions fx and gz are alternated. One time you are optimizing one function, next time you optimizing the other function. So, and you're feeding it with the previous solution you got from the previous function. So a separable function f or g will allow the distribution of pieces for minimization in parallel. Okay? So once you separate, you can distribute these pieces into parallel computers. Okay? So there are three main steps, in fact, for each x hat, z hat, y hat, which is kind of our target or the optimal solution. First of all, you see when we write argmin with respect to x, what does it mean? It means that we are looking for the minimum of L row here. When we're looking for the minimum of L row, I think it's kind of, let me check the textbook. It's a typing mistake from my part. Should have been max. No, it's okay. We're looking for the, I think, so that's a typo from their part. Okay, because they are talking about maximizing. I assume from now on, guys, on tape, let's put it on record that I think it's this contradicts the fact that I'm talking about maximizing. Yeah? Okay. So I think they are maximizing, either maximizing both or minimizing both. Okay? You got it, guys? So basically here we are looking for the arg. Let's say that this is minimizing it instead. Are you listening to me, guys?
Do you mean either maximizing both or minimizing both?
Yeah. This cannot be, it is a contradiction, as you see, okay, in the textbook. So either you are doing minimization, so you'll be looking for the argmins, x and z, or you're doing a maximization, you're looking for the argmax. In all cases, what I wanted to say is that when I do the argmin, when I ask for the argmin, I'm asking for the x that optimize a row. Okay, got it, guys? So that's why the separation is set. So you start, for example, your initial iteration with a given zk, yk, or prefixes if you just pre-initialize them, and you find the xi that minimizes or maximizes the error, and this is going to be the new value of your xk. Okay, got it? Then what can you do? You will take this xk, you just obtain it, and you put it here. So now you are working on minimizing what? A row, but z is the variable for the minimization or maximization. Yk is still the same as initially preset. So once you got the new zk plus 1, you take both xk plus 1 and zk plus 1 and you insert them here. Okay? For the step size, what can you do? What are you going to do? You are adding to yk for updating and obtain yk plus 1. You're adding row times the difference between axk plus 1 plus bzk plus 1 minus c. Okay? Which is, in fact, the difference in terms of proximity or closeness to what? To fitting or satisfying the conditions that ax formerly equals b, or now ax plus bz equals c. Got it? Is it clear, guys? So now we have a little experience with these kind of numerical algorithms, how things can be done. Got it, guys? Okay. So maybe I'll do a small example if we have time, but let's leave it to the last part if we have. Okay. So any question on this, guys? Is that clear? I will dig on this, but I'm pretty sure that it's either minimizing or maximizing. Doesn't make any difference, but arguments should be consistent with the objective we knows above. So some remarks. Now, some remarks about the ADMM. In fact, it could be quite slow to reach a solution with high accuracy. But in fact, at the same time, it's surprisingly fast to achieve acceptable accuracy. In fact, this is in fact quite typical of these kinds of well-inspired methods. Like the most basic ones we see in operations research, the simplex algorithm. In theory, this could be very, very slow, right? But in practice, it converges quite rapidly using the lexicographic rule. You can converge very, very rapidly. So let's mention here also that, in fact, in the context of deep learning, we'll see, inshallah, in chapter 7, modest accuracy is often sufficient and even desirable, in fact, to avoid what we call overfitting situations. To avoid in situations where overfitting the training data leads to unhappy results because you are, in fact, too much inspired by training data and you are not able anymore to get the flexibility needed to react to new data, to new patterns. You got it? Did you get the point, guys? So sufficient, let's say, or modest accuracy is often enough in deep learning. In fact, Floyd and co-authors, they did some improvement to the ADMM algorithm. They, in fact, used a new variable they called U, which is equal to y divided by rho. Okay, this should be rho. To rescale, in fact, the dual variable y using u equals y divided by rho, and combine the linear and quadratic terms in the augmented Lagrangian just seen. And this produces what we call the scaled ADMM version of the ADMM, which has many advantages in practice. Okay, so in fact, they work on that part of f to get the axis, as previously mentioned with the ADMM. Plus, in fact, the z here is fixed. The u, of course, is prefixed from the initialization. Okay, so there is no longer y. It has been substituted by over rho. And you add the square term instead of having a linear term. Okay, instead of having an exponent to and the power 1, you can add a square term. Okay. So in this way, now we add, in fact, the fact that once you get the xk plus 1, you get it and find the z. That minimizes the g of z here, not g of x. Okay, and once you got the xk plus 1 and zk plus 1, what could you do? You can now use them to do what? You see now this part, the last part, where you have to find the use of the y's is much more simple, because now you've used the square of the error here, so there is no. Now you can just write uk plus 1 as uk plus ix plus 1 plus bzk plus 1 minus c. So there is no rho anymore, okay? Which is much more simple. In fact, it has been shown that it has some computational advantages compared to the original ADMM. Okay, guys? So this is for the closing remarks about the ADMM. Now, we'll have, if we have time, we'll do a small example as we did previously with the Lagrangian method and the dual decomposition. Okay? But my intention is to try to finish this section today. So I'll move to what we call matrix splitting. And this reaches the issue that has been raised by Abdulaziz this morning, and Abdullah Baroum before, and other colleagues. In fact, the idea is that the splitting in matrix. So the first connection, in fact, of AX equals B to the ADMM comes from the splitting of that matrix into A equals B plus C. In our case, if you remember, we were willing to split A and the homework of the splitting of the matrix to S plus T, right? So in fact, in classical examples, as in the example we've seen in class, we could use the diagonal part of A, as I did. And I've shown you last part that if you use the diagonal part in the homework exercise, it's not good because it cycles. Okay? So one idea could be either to take, for example, a lower triangular part of A, for example. So this is even an idea. And this is called what? Colony or Gauss-Seidel splitting. Okay? Or to take just a small modification on the diagram, and it works perfectly. Okay? Those who have tried this already succeeded. Okay? So this is a remark that reaches our observations about one of the exercises. I think it was exercise 5. Guys, let me check. I think it was exercise.
I think it
yes.
was 2, Doctor.
Yes, exercise 2. I think it's exercise 2. Yes, of course. Okay. Guys, you have something to add? Okay, so exercise 2. Aziz, something to mention?
Yes, Doctor, regarding to the, could you please explain this point again? The classical example that.
Yeah, my pleasure. So in the classical example, we use the diagonal part. For example, if A, let me, can I take the whiteboard, guys? Yes, why not? So if I'm trying to solve, for example, AX equals B.
Yes, yes.
Okay. Okay. So if I'm I'm trying to solve AX equals B, for example, with A equal to let me say 2, 1, 4, 4, 2, 1, and 1, 4, 2. Okay. Okay. And I'm trying to write it as what? As S plus T. Okay. And this S is the one that is giving me a nightmare. Which, how can I use X? How can I define X? Okay. So one of the ideas is to take, as they say, take, as we did also in class, to take just the diagonal part of it. Got it? Okay. This leads to two possibilities. It works. I'm happy. Okay. It works. I mean, I can see it numerically. It works. I'm iterating because you have the code to do that. I already have to do it, so I'm happy. It doesn't work. Okay. If it doesn't work, I have to dig on it. I can either do a perturbation. What do I mean a perturbation, guys? We did small perturbations in the inversion in section, I think 3.1. Small perturbation, just add one item here, one item there. Okay? Stay quite close to the diagram. Okay? Or for example, just multiply it. Make the diagonal quite large. For example, I can say take this matrix. Take K times S. Okay, it might work. One of the advantages, for example, here is to make the determinant large. And if you make the determinant large, you get to the fact that the norm of S inverse times T is quite small, very close to 1. Right? Might be even less than 1, which means you have faster conversion. Get my point? Why am I doing this? Because now you see the determinant here is 8 to the power 3. But if I multiply, let's say, by 2, and now I have 4 power 3. 4 to the power 3 is quite huge. 16 times 4, 64. Okay? So the determinant is higher. So the S inverse will be divided by, would carry 1 over 64, 1 over the determinant of S. Got it? It might work. The other way, as I mentioned here, the method is to do what? To take a lower triangular matrix or an upper triangular matrix, which means the computation here is much easier for the conversion or for the solution of the system. Lower or upper triangular, both should work. Huh? واضح يا عبد العزيز? Is it clear for everyone, guys? Okay, guys, I take note or just leave it. Okay. Hopefully it's clearer, guys. All right? Any question on this? Okay. You still hear me, guys? Okay. I'll go back to my things. No comments? Oh,
Yes, we can.
okay. That's wonderful. Yeah. Wonderful. Okay, so let me go back to my things, guys. So we're talking about the splitting of the matrix, and okay. So a first connection of AX equals B to M comes from, in fact, from splitting the matrix A. Last kind of examples, we said that B could be the diagonal part of A or the lower triangular part of A. Okay? In fact, those ideas were improved by Douglas Ratcho, and now the Ratcho that plays with the England side of football team, and Peaceman Ratcho, who regularized by adding what we call it's alpha I. Should have been written alpha I. Okay? Alpha I, and alternated between B and C. Okay? So in fact here, what they're trying to do is to use the ADMM to solve, not to optimize function fx or f of x plus gz. To iterate between x and z and try to solve the system by the ADMM. Okay, so we remove that optimization part. So now assume that you start with an initial z0. You can compute the corresponding x1 using the matrices you've chosen, C and D, or S and T in our case. And then you take the xk plus 1 and you put it back here. Okay? Then you compute the z and you go back. You see, the idea now is that you can still use the ADMM methodology to solve a linear system. In fact, this idea appeared to lead led to deeper nonlinear ideas, what we call proximal operators and monotone operators. So we have another version, in fact, of the ADMM, we call the proximal. So a special feature here is the appearance of exact formulas for several important proximal operators. What do you mean by exact formulas? That we were able, using this, to obtain closed form solutions, which is huge. So we no longer rely on numerical solutions. We obtain closed form solutions for our optimization problem. So particularly when with the L1 minimization that lead to soft thresholding and shrinkage. So here I'll be given an example. So for example, example 2, page 203, says that an important L1 problem, okay, has the exact solution where f of x is equal to lambda times the L1 norm of x. So lambda is multiplied by the just the absolute values of the x's, as you see, which splits, as you see, into n scalar functions lambda times the absolute value of x and xi. So in fact, the separation by the ADMM leads to the minimization of each special function f1 to fn into this form. So you're just adding this quadratic term, rho times xi minus vi, okay? Where vi is just zi minus ui. Okay? Now, I hat would be equal to, I'll just explain what does this plus subscript mean. Is vi, so this is the closed form solution. It's vi minus lambda over rho plus minus vi minus vi minus lambda over rho plus, which is in fact vi minus lambda rho plus. In fact, to understand this, you need to understand the subscript. In fact, when we write this vi minus lambda over rho with subscript plus, it means we are taking the maximum between vi minus lambda over rho and 0. Okay, so if vi minus lambda over rho is negative, we'll take 0. If vi minus lambda over rho is equal to 0, you still take 0. If vi minus lambda over rho is positive, then you take vi minus lambda over rho. Okay. So in fact, what does this? What this is intention is to do what is to take the absolute value. Okay? So the absolute value comes from here. Okay? Those who did some more advanced, like non-linear and linear programming courses, they know, for example, that fact that you are willing, for example, to under some conditions, if you are putting just a variable where you would like to minimize or maximize on some closed set or convex set, z equals to, let's say, absolute value of x. Now, this objective, guys, is it linear or non-linear? I'm willing to minimize z or maximize z. I would ask you to dig deeply in your memory to think of it. Is it linear or non-linear? This is the x-axis. Absolute value of x is piecewise linear. Okay, you got it? It's not differentiable as you know. But from non-linear programming or linear programming point of view, this is a headache as it is. Why? Because this is not linear. I mean, there is something that has to be done with the abstract. So usually what we can say is that the absolute value of x is in fact the maximum between what and what? It's the maximum between two values, which are x and minus x. Am I right? Yeah?
Yes.
So in fact, the absolute value is the solution to which problem? Where you're trying to maximize z, to minimize z, with the conditions that z is larger than x and larger also at the same time than minus x. Okay? So this z, in fact, you get when you try to optimize, that's the small function, the small linear program. You minimize z with z larger than x and at the same time larger than minus x. It means that you would stop at the highest value between x and minus x. So this is x, this is 0, and symmetrically, this is the minus x. So if you're minimizing, you'll stop at the largest value. And of course, when x is negative, just an inversion, you will stop at minus x. Okay? So you were able to realize this objective, absolute value objective. Okay? Absolute value, in fact, is just a solution to a linear program, a small linear program. Okay? So I just wanted to hint or to pinpoint the fact that when I'm writing this plus subscript, we are talking about getting the maximum value between 0 and I minus lambda ti. Okay? By the way, this opens another window. What should be done, in fact, in optimization, if I had free variables? Do you recall anything, guys, from that? What do I mean having free variables? Variables like variables that are not to be non-negative. For example, in a cooling or heating problem, I might be asked to set a variable, a decision variable that is the temperature. Okay, and temperature could be either positive or negative. Right? So, but basically, almost all optimization algorithms are positive optimization problems. So the decision variables are asked to be positive. Now, what one can do is a simple change of variable. What you can do is something that is quite close to this. define x to be, for example, equal to y minus z, with the condition that both y and z are positive, mean non-negative. Okay? So what happens, of course, now the column of the variable x, which was supposed to be free, is doubled. You have similar column for y, but the -1 times the same column for the new variable z. Okay, you got my point? And now, with the optimization automatically, so you're just adding one column, and automatically, if x is negative, then the y should be 0, and the z is positive. And if x is positive, then the z would be set to 0, and the y is positive. Okay? So this way, you have, in fact, avoided working with free variables. Okay? So these were two remarks I wanted to add in case you are facing similar issues with some optimization problems. Okay, so in fact, I was talking about what the ADMM brings here with this small exercise. Okay, is that in fact not only is this thresholding function had solution we found an explicit solution, but in fact it is an important linear solution to an important solution to an important nonlinear problem, which is this one. Okay, and it has in fact it's also a shrinkage operator where every vi moves towards 0. Shrinkage is very important in statistics when we talk about the lasso optimization in the least square. Okay? So let me try to wrap it up. So the new version of the ADMM. So in optimization, the analog to those matrix operations, in fact, we've seen in 26A and 26B, we've seen with the split of A into B and C, has B equal to 0 and B, capital B, equal to gradient of F2. Okay? So here F2, in fact, is the L2 norm part, and its gradient of F2, or its subgradient if necessary, is effectively linear. So then, in fact, the gradient partial or subgradient of 2 plus alpha I corresponds to B plus alpha I. And its inverse is what we call the proximal operator. So the proximal operator V is the argmean of f of x plus 1 half of rho times the L2 norm of x minus phi. Okay. So the key facts, in fact, to justify this proximal approach and the splitting in F1 plus F2 are that the L2 norm is well understood and fast to move, and the L1 norm problem often has a closed form solution. What do you mean closed form solution? An analytical form solution instead of a numerical approximation by shrinkage. So this is the algorithm, the proxy ADMM, with a scaling factor alpha. Well, in fact, we try to solve this system at x equals b using the splitting into b and c, and now b is equal to gradient of f2. Okay? Or you may even use delta f2. Okay? Got it? And it works just fine, and then you update it like we've seen in the ADMM version of the solution of the linear system. Okay? So I'm just left with additional information. So first of all, we need to understand what is a Bregman distance. So usually in reality, guys, distances between 2 points are not always equal. So in fact, the Bregman distance is an increasingly important idea in many applications. It has the unusual feature that there is a lack of symmetry. So between 2 points U and V, the distance from U to V is not the same as the distance from V to U. Okay? For example, a Uber optimization problem. Okay? Karim, I call it here. Okay? Or for example, an let's say hunger station optimization problem. Talking about real life application, guys. The distance between 2 points is not the same if you go from one direction or backwards or coming back. So the distance from U to V depends here in our Bregman distance definition. Depends on a function f. we do have the distance that is positive, of course, and the distance on a straight line is defined such that the distance from W to V is less or equal to the distance from U to V, of course, if we put them on a line. Okay? That's the only condition that we need to satisfy. I don't know what's happening with my pen today. So you see the Bregman distance writes this way in general. The distance from U to V is Fu minus Fu Fv. So it uses this kind of function minus the gradient of F at V U minus 1. Right? So always the gradient F is replaced by separated. In fact, at points where the graph of X has a corner, what do you mean by corner? Where the point is not smooth, what the function here is not smooth. So the function is not differential. Okay. So the differential F can be the slope of any tangent that stays below the complex function. And the last notes I want to add are about what is called the split Bergman and the split Kacsmarz algorithms. So for the split Bergman, we taught linearized Bregman iteration with parameter lambda, which is positive. We start from our original system, Ax equals b, and iterate. Okay? We iterate using this updating scheme. Let me correct it. I see a small typo here. It should have been written this way. Oh no, it's okay. It's right. So it's yk minus sk at times axk minus b. Okay? So this is the way you update your y's. And once you updated the y's, you can use them to update the axis. Okay? Or if you want to call them differently. So in fact, sk is the sign of yk, so positive or negative, minus times the maximum between the absolute value of y's minus lambda and 0. So you take the positive part, kind of absolute here. And the Kacsmarz iteration, the counterpart, is an effective methodology or method used for big data with sparse vectors. And it starts also by solving Ax equals b, and it cycles sequentially or randomly through the n equations of Ax equals b, so those written as ALT x equals bi. And each step, as you've seen probably from the homework if you try to work on this, so each iteration does what? It adjusts xk by a multiple cai of one column at to satisfy the ith equation ait xk plus 1 equals bi. Okay? So this is how the split Kacsmarz solves. Okay, so xk plus 1 is xk plus bi minus iit xk divided by ai, the norm of ai squared. Okay? Once you solve this, you can take the solution, and so this solution, in fact, solves this equation. So that's it for today. We'll hopefully have the time to go backwards and try to at least to see one example, inshallah, next time of the split ADMM before entering chapter 4, which deals with more advanced things. Okay, so